Hello, everybody. All right. Section 4.8, the very end of Chapter 4, about applications of exponential and logarithmic functions. All right. Now, we've done a whole lot with exponential functions and logarithmic functions in this chapter. We're finishing here with some word problem type things, basically, in which this is the first goal. There are two. You will write and use equations to model exponential growth problems. And then the next goal will be that we'll do the same thing with exponential decay problems. And if you don't know what those are, you will know after watching these videos. By those, I mean exponential growth and then exponential decay later on. Okay, so exponential growth, exponential decay. First thing we need to talk about is what is exponential growth. And this is a definition I'm going to need you to write down. Exponential growth is when a quantity grows exponentially if it increases by a fixed percentage over regular time intervals. All right? If it grows by a fixed percentage over regular time intervals. Now, a couple of examples. Say you have an account balance that grows by 2.5% each year. So since it's growing by a certain percent over definite time intervals, that's exponential growth. Another example, population works a lot with this. A bacteria population increases by 0.35% each day. There's a percent growth that a quantity is growing by, and here's a time frame, a regular time interval over which it grows by that percent. Okay, exponential growth. Well, there's a formula associated with exponential growth that I want you to know. And it's the formula that you see on your screen, and then we're going to use that in order to write an exponential growth equation for the problem that you see below. Whenever we're talking about exponential growth, you have an original quantity that we're working with first of all. And that's what this lowercase a is going to represent. And then the idea is that you're using an equation that takes the initial quantity in order to figure out what a quantity is after a given amount of time. So I'm going to label this capital A. Let's say it's an updated quantity, for lack of a better term. Or rather, I'm going to say current quantity. All right, now when you see an example of an exponential growth equation, you'll understand why the 1 is right there. This R is the rate of growth. Remember, you have a fixed rate of growth over fixed time intervals? Well, so R is that rate of growth. Which, by the way, must be written as a decimal, not as a percent. So if the growth rate were 7%, you would write 0.07 for R. All right, and then finally the X, or the exponent, because it can actually have several parts to it sometimes, represents the number of regular time intervals that have elapsed. So I'll put elapsed time for that. Alright, so the equation calculates the current quantity of whatever it is that's growing exponentially based on the initial quality, the growth rate, and how much time has passed. Whether that's in days, months, years, seconds, depends on the individual problem that you're working with. Alright, so let's take a look at this problem. It says that a population of 20,000 grows by 1.7% per week. So there's our fixed rate of growth over a fixed time period. That means exponential growth. Write an equation to model this growth. Alright, well, it's quite simple if you just kind of use the formula that I wrote above. Alright, well, we're going to say the amount A is equal to the initial amount. Now, the initial amount here is 20,000. I'm just going to write 20, and then I'll just specify that it's in thousands later on. So we'll say the initial amount is 20 times 1 plus the growth rate. And remember, I said that the growth rate you got to write as a decimal, not as a percent. So you got to move this decimal point 2 places to the left. That's going to be 0.017 to the x power. Alright, and then we're going to simplify that. Actually, go ahead and add the 1 and the 0.017. So you get 20.017 to the x power. All right, now, basically, the way the exponential growth works is you have to repeatedly multiply some quantity by a number that's bigger than 1. In this case, we're going to repeatedly multiply by 1.017. When you multiply by a number that's bigger than 1, the product gets bigger, right? And so we're just multiplying by 1.017 x times. Anyway, that's an exponential growth equation. If it were exponential decay, this factor that as we would call it, the base of our exponential term, would be less than 1, not greater than 1. All right, let's see an example of how these exponential growth functions work. All right, you're going to want to copy this problem down, so pause the video if you need to do that. One application of exponential growth is that for account balances, credit cards, savings accounts, lots of different applications financially for this. This problem is about a credit card. It says a credit card balance of 16,000 dirhams grows at a rate of 11.2% annually and asks how long will it take for the balance to reach 25,000 dirhams. Now that's assuming that there's no attempt to pay off the balance. It's just left to grow over time. Well, because we have an amount that is growing by a fixed rate over a fixed time interval, all right, annually means every year it grows by 11.2%. That means we have exponential growth. And so we ought to be able to write an exponential growth equation to model the problem. And once we have that, then we can figure out how long it takes before the account balance reaches 25,000. So let's go ahead and work on that equation. All right, the amount A in the account would be equal to the original amount, which we can write as 16 for 16,000, times 1 plus 0.112, that's 11.2%, to the x power. Or 16 times 1.12 to the x power, 1.112. Okay, now if we're trying to figure out how long it's going to take for this balance to reach $25,000 or dirhams, we want to know how long it's going to take before the value of A is 25,000. So for this problem, we're replacing A, the capital A, with 25,000. So that'll look like this. Here's the work now for the problem. Oh, except that since I wrote 16,000 as 16, I better write 25,000 as 25. All right, and so what that leaves us with is an exponential equation, right? The variable is an exponent. And how do we solve exponential equations? Well, we take logarithms of both sides. So let's take a common log or a natural log, your choice. I'm going to take a common log of both sides of the equation, and then let's just see how the work plays out. Now on the right side, where we have the logarithm of a product, we're going to separate the two factors of that product. And at the same time, I'm going to use the power property and put that x in front of its logarithm. So that'll be like this. All right, so you see I separated the product like I said I was going to do, brought the exponent in front. And now in order to solve for x in this equation, what I'd like to do is get all the terms that don't have an x to the left side of the equation, and then I want to divide by the log of 1.12. So we're going to subtract the log of 16 from log 25, then we'll divide the result by log 1.12. That'll look this way. By the way, I realize that I've been leaving out a 1 from this 1.112 over here. So these should all be 1.112s, right? Because it was 11.2%. That's what we wrote right here. My mistake there. All right, now this kind of question really is a calculator question. If we want the exact answer, this is the exact answer. But that doesn't have a lot of meaning to you. So just go ahead and type that into your calculator and let's figure out how many years it takes, because our time was measured in years here, for the account balance to reach 25,000 dirhams. And so the three significant figures, you end up finding out that it would take about 4.20 years in order for the account to reach that balance, right? Okay, let's go for another example of an exponential growth problem. All right, in this one, in a small village, it says there were 20 people infected by a virus. The number of infected villagers grows 6% each day. So the time frame here is not years, this time is days. We're going to be asked several parts. This is an IB style question. Several things about this village where there's people that are infected with this virus. And we're going to start off by this. We're going to ask how many villagers are infected after 2 days and then after a week. And in order to answer that question, how many villagers are infected at any given amount of time, we need to write an exponential growth function to model the growth of this virus, or the spread of the virus, if you will. So go ahead and write your function that models the growth of this virus. Hopefully you're starting to get pretty good at this already. It's a simple pattern, isn't it? Put the initial amount, which this time really means 20, not 20,000, and then do 1 plus the growth rate, which was 0.06, so 1.06 to the x power, where x in this case is going to represent the number of days that have passed. As such, when we're answering part 1, which asks how many villagers are infected after 2 days, all we're going to do then is we're going to find out what a of 2 is. Plug in 2 for x. And then type that into your calculator. Let's see what we get. All right, you get about 22.5 people. These are people that we're dealing with here. Now you can't actually have a half a person, can you? So let's just say if we have more than 22 people infected, that we've got a 23rd person infected. They might not be fully infected yet, but if you were in that village, you wouldn't want to be near that person, right? So we better count them as infected here. All right, about 23 people so far. And then if we want to figure out how many are infected after 1 week, well, keep in mind that the time here is measured in days, so you have to plug in 7 for x, because it would have been 7 days. Do that real quick. And you get about 30.1 if we follow the same guideline we did before, where any more than 30, any more than a whole number, we're going to round it to the next one. Then we're going to get about 31 people are infected, at least partially. The 31st person is. Great. So let's go on and answer a little bit more about this problem. Next thing it wants to know is how long would it take before twice the original number of villagers are infected. Now remember, originally there are 20, so we want to know how long will it take before there are 40 people infected then. And so in our equation, we're going to replace the capital A with 40. We'll say that that's equal to 20 times 1.06 to the x power. And now this becomes a lot like our example where we had the credit card balance. We're now trying to figure out the amount of time that goes by before we reach a certain quantity. And so we're going to have to be solving an exponential equation. We're going to use logarithms to do that. So take the log of both sides, solve the equation. Let's see if we get the same thing in the end. All right, I'll check in with you after each step. I've taken the log of both sides, a common log of both sides. Now let's separate this one using the power property again. As such, then, to get x by itself, you got to subtract the log of 20 from both sides, and then divide by the log of 1.6. Well, here's what that looks like as an exact value. In fact, we could even take it one more step as an exact value, because we could combine these two logarithms into a single logarithm like this. All right, just use the quotient property to make that log 40 minus log 20 into a log 2, and then do the division. And you'll get about 11.9. Remember, the units here were time in days, so you'll put days for the units there. And you can have a part of a day. We don't need to round that up to 12. 3 significant figures will be good here, as normally they would be. That's exponential growth. There's going to be a video about exponential decay next. Thanks for watching. See ya.